Thank you. Hi, everyone. This is, we have KubeCon, which obviously is my favorite conference of the year, but this is probably right number 2. One, you get to see all these people in this great environment. 2, it's in New York, city of my previously living before I came to Seattle. But the best part about it is you get your own walk-on music. I feel like a professional wrestler. Yes, I'm here to talk about Kubernetes 1.5. You'll forgive me, I'm just a PM. I neither write code nor build and donate incredibly large clusters or run workloads at enormous scale like Ticketmaster does. But I'd like to talk to you a little bit about what's in Kubernetes 1.5, which we'll be launching this week, and then beyond. This is one of my favorite slides. I give it every time I give one of these keynotes, and every time I move the chart up and to the right. This is the number of commits since July of 2014. It's crazy to think that this started, the entire thing started just 2.5 years ago from Brendan and Craig and Alex and all the folks here at CoreOS and Red Hat and so on and so forth. The line just keeps going up and to the right. And as you saw earlier, we just crossed 40,000 total commits to the project since getting started, with 1.5 coming this week. Some of the big names that you see up here, over 4,000 commits in 1.5. And that's with a shortened schedule. We released the previous one just at the end of September, and we cut it short so that people could actually go home for the holidays. I know, very foolish. Another 25% in unique contributors to the project, top 0.01% of all GitHub projects, and 3,500 external projects based on Kubernetes. And that last one is probably the one I'm most proud of. It's not just a platform for itself, it is a platform that other folks can build on top of. You can see just a few set of the companies contributing, and at the bottom there, the number of companies who have been out there publicly using. It's really hard to overstate this. You see this time and again across a wide variety of different industries. So you have something on the order of like 5 of the top 10, or 15 websites in the world using Kubernetes either in whole or in part. Major game manufacturers are using it, left, right, and center, including Pokemon Go. You see huge media streaming organizations using it, such as Comcast. Some of the largest GPU, ML-based clusters in the world are based on it, including OpenAI, and Google's own Cloud ML, the service that we offer for customers, is running on top of Kubernetes as well. So these are enormous projects, and we're very, very proud of them. I also put this up every time. I like to restate it. There's this apocryphal, potentially true story that everyone who comes to Google for the past 15 years would come on and have this productivity cliff. You'd come on, you'd join, you'd say, wow, there are a lot of smart people here, this is going to be a lot of fun, and then you'd do nothing effective for the next 6 months. And the reason is because when you were coming from the outside, the tooling, the experience was so different than what you were using internally to Google. Google's been using containers for about 15 years. Some of the Google engineers were some of those who contributed upstream a lot of the code, and not just exclusively. There were people from IBM and a wide variety of people into the Linux kernel. But what we wanted to do when it came to Kubernetes was really reduce that cliff, to give everyone the power to run agile, reliable, distributed systems at scale. And that's really the impetus that Brendan and Craig and others took on when they first launched the Kubernetes project. So with that, let's talk about Kubernetes 1.5. There are many, many features in Kubernetes 1.5. I will absolutely not go through even a quarter of them. I did want to highlight, though, particularly because this is such a large enterprise-heavy conference, some of the features that are really relevant to doing exactly what I described before, really up-leveling your systems to support these enormous distributed systems at scale. I'll talk about simple setup, including multiple cluster simple setup. Sophisticated scheduling, which is something that really unblocked a whole bunch of workloads at Google. We'll talk about network policy, which is something that has been contributed mostly from the community, but has really come into its own. And then we'll talk about Helm and some of the ways to do even complicated application installation at scale. So I'll re-review this. One thing that people have heard a lot of is setting up a Kubernetes cluster is hard. Anyone in this audience? Show of hands. Anyone here that setting up a Kubernetes cluster is hard? Yeah, the rest of you are liars. The fact is that if you went down a straight and narrow path, there was an incredibly simple way to do it. It's called KubeUp. It's built in. It's ready to go. But most folks, particularly those in this audience who have very large deployments, need to do customization. You can compile from head. You can unwind the KubeUp tool, which is just a big, long 2,000-line bash script. That sounds easy. Or you could use a third-party tool, of which there are many, and they are very good. One contributed by CoreOS, one contributed by the community. There are lots of them. However, we felt like that was really a mistake. The fact that this was built from the outside coming in, that's really not a great fit for us. So we wanted to bring that into the core of Kubernetes. And in Kubernetes 1.4 and now in 1.5, we have launched a tool called kubeadm, kubeatom, one of the pronunciation arguments we'll have for many years. So I'm actually going to walk you through setting up a Kubernetes cluster on a single slide. You can see there, you can install from packages, super simple. You run kubeatom init, presto, you have a Kubernetes cluster. That's it, seriously. You have a one-node Kubernetes cluster. It's running a master. When you want to run a single node, you go down here. You install the exact same packages. You type join with the command that was spit out at the last one. Presto, you now have a two-node Kubernetes cluster. That's it. Seriously. And then lots of folks, you're using things like overlay networks or complicated networking. In this case, I'll use something contributed by the Weave folks. You type this, and on each node, it configures a daemon set that runs and configures your Kubernetes cluster. So now you have not just a two-node cluster, but one using an overlay network that might conform to your policies. Really, really powerful stuff. OK, so that's setting up a cluster. Who has multiple data centers that operate smoothly and have no trouble setting them up? Wow, we have some brave souls. Very impressive. Most folks don't, including Google, by the way. It is really hard to do this right. But in fact, that is part of the tenet of Kubernetes. The fact that you can set up Kubernetes in all these places gives you a common deployment fabric, and then you can reuse that and connect them all together. So we are now launching kubefed. So setting up a Kubernetes federation. I will do this on stage for you. First, you type init the name of your Kubernetes cluster or federation, which I've called fellowship, the cluster context, which in this case is Rivendell, and a DNS. Presto, you've created a federation. Then I type config, and I use that config, or I use that context, and then finally I join a second cluster to that federation context, and I'm done. I now have a federation with two clusters talking to each other. Now you're saying, wait a second, that's crazy. How did you handle all the security, etc.? That is true. But as you notice, I'm doing it from a single command line where theoretically I've already downloaded those credentials, much like you would today, and switched between them. So this isn't magic. The exact same permissions that you have for allowing people to download and configure clusters is available for you. And so this last one is the killer. I want to now deploy a single application across this cluster. Boom, done. Now, this is, in fact, something that is better than we do at Google. Today, at Google, you connect to all these multiple Borg cells. It's annoying. We have all this insane tooling. I would argue that we're starting to reach the point where we're surpassing even the invention that this was based on. OK. So now I'm going to get into a second thing. Now that you have all these clusters, Today, you might set up multiple node pools, or you might set up individual clusters. But that's a bit of a mess when it comes to things like GPUs, when you have high mem machines and low mem machines, high CPU, low CPU. You can already get through scheduling this and assigning things directly. But the unfortunate part is that it just becomes really complicated. How do you set this up? How do you keep everything in sync? If one GPU machine goes down and another one comes up, how do you make sure it has the right label? Didn't you start using Kubernetes to avoid all this thinking about machines in the first place? Yes, you did. And the way you solve this is with sophisticated scheduling. So let me walk through some of the scenarios. I'll do it from memory. We don't need to go back. There are three things involved here. One is taints and tolerations, and I'll explain what this is in a second. Two is forgiveness. And the third is around disruption budget. So taints and tolerations. The first thing you want to do is you want to be able to describe a machine using the same language you use to describe any other object in the system. So in this case, on the left-hand side, you have a node that has 4 GPU plus 2 GPUs on it, or excuse me, 4 gigabytes of memory, 2 GPUs on it. On the second and third one, you just have 4 gigabytes of memory. Let's say I have a pod. That pod needs 4 GPU. I can go anywhere. That sounds great to me. That's obviously not good, because now it's sitting on something that it doesn't need all the hardware for. The second pod comes along and says, got to give up. No GPUs for me. Or, and that's in the best case scenario, where you've actually described the GPUs properly. If you describe them wrong, it says, well, I can just go anywhere, right? Because I don't see something that matches me. But then you have one very unhappy pod. That's not good. So the better way to do this is with what's called a taint. This is basically where you paint a metadata against a node. You say, in this case, I want to paint this node with a GPU, and I want to say, if no one is able to match this, I would prefer that people don't schedule to me. So exactly the same case. I say I have a pod with no toleration on it, and I'll show what a toleration looks like in a second. It says, well, these 3 machines sort of match, but I'm going to prefer to schedule stuff not to GPU, and it does so. Then the GPU pod comes along, and on that you've said, hey, I have a GPU. Try and match up to this. If you can't, try not to schedule. And that's what it does. It looks at both these, and it says, there's this great spot. It's a perfect fit. We are both happy. OK, so super powerful. In the language you use to schedule the rest of your workloads, you're able to do this kind of workloads. You don't have to do anything underlying to the node. You don't have to have startup scripts or anything like that. This all is within the context of the system. Extremely powerful stuff. And I'll go through a couple other examples here. In this case, let's say you have a premium set of nodes where you always want to hold things in reserve. Let's say you have, you want 20 CPUs that are always in reserve for a certain set of workloads. You can paint those. In this case, these 2 premium pods can go anywhere. Let's say, for the sake of argument, that one goes to the premium and one goes to not. Then a regular pod comes along. It's not going to schedule to that. So again, extremely powerful stuff when you want to do this, and you don't have to create multiple clusters to accomplish that. Let's use a trusted platform from CoreOS, for example. In this case, I want to schedule a pod, but I want a rule that says, unless the node is available, I'm not going to schedule. And I'm not going to, this system is not going to paint that node as being available unless it's past the trusted platform module. So in this case, the node, when it starts up, it goes, it checks with the trusted platform module, passes back, the taint is removed, and then the pod can be scheduled, which it does. And then let's go to a final one around taints and tolerations. This is where the hardware is failing. In this case, you have a system where the disk begins to fail. It creates a notification. It tells the API server, hey, this disk is failing. The API server says, first, I'm going to taint the node to make sure nothing can schedule. And then second, I'm going to schedule a new pod onto the second node there because I'm going to treat that node as failing. The pod continues to respond until the node fails or the new thing has been scheduled. OK, So that's taints and tolerations, extremely powerful stuff, and it lets you start to operate in ways that respond to the business and the workloads that you have running on it. Second is around forgiveness. So we talked about this earlier around some of the stateful workloads that folks are starting to run on Kubernetes. And it really requires understanding what's going on with the system. So in this case, you have something called forgiveness, where, oops, I skipped forward just a second. So like first, the system is all well, and it's the API server is getting regular updates. At some point, let's say a node stops responding. Well, you don't want to kill it right away and start rescheduling new nodes, because maybe it was just a network partition and that's OK. But you have two workloads there that have different sets of requirements. In this case, you want one pod that responds after 5 minutes and one pod that says after 30 minutes I need to reschedule. So in this case, I haven't heard from the node in 4 minutes. Now I haven't heard in 5 minutes. Uh-oh, I got to do something. So the first thing I'm going to do is I'm going to treat the pod as being dead. It's still there, and it may still be responding, but I'm just going to treat it as dead because I haven't heard from it in 5 minutes, and the node could have gone away. And then I go and schedule a new pod. Then the second one, it's been another 30 minutes, and then I'm going to treat the other pod as dead and schedule a new one. And presto, now the system is back. Now if that node comes back, those pods are there, we've already treated them as dead, so we're just going to kill them when they come up. And again, this is extremely powerful stuff because it means that I don't have to build in all kinds of custom logic to support this, network partitions, things that happen all the time in data centers. But the system doesn't overreact as well. And then finally, let's talk about disruption budget. So on a 2-node cluster, obviously, it's very easy to schedule and manage your workloads. As fleets start getting very, very large, particularly with things like stateful sets that need things like quorums, you don't want to wipe all the machines at once and then bring them back. In this case, we're going to use something called disruption budget. Again, a first-class object built into the system. So in this case, I'm saying it's time to upgrade to Kubernetes 1.5. I tell the API server, all right, evict A and go to work. So it goes, it tells A to begin shutting down. Now let's say pod A requires, 5, 10 minutes to shut down properly, clean its disk, and so on and so forth. I may not know that as an end user. And so I say, OK, let's, we're done with A, or A is beginning to shut down. Let's evict B. But I've set up and said, look, I don't want all of a system to come down simultaneously. I want only one node out of the system, or excuse me, one pod out of the system to come down at a time. So in this case, the API server understands that, says, sorry, can't do it. Wait. The new pod gets scheduled over to A. The disruption budget is now met. And then now I can evict B. So again, on a 1,000-node cluster where you may have 200 nodes handling Cassandra, you don't want all 200 going down simultaneously. Maybe you only want 10 at a time going down. That can all be built in. OK, so that is a disruption. That is some of the sophisticated scheduling, which is all landing in Kubernetes 1.5. Let's talk about a couple other things. The first is around network policy. So today, you might do this with VMs and IP tables and firewall rules. A very common scenario is where you might have a 2-tier app. You might have a front-end app. The front-end app can talk to the back-end app. But there's no reason the back-end app would ever need to talk to the front-end app. So you would do this by saying, well, these are the front-end. Green is the front-end. Red is the back-end. I'm going to say it's OK for the green to talk to red. And I'm going to say it's not OK for red to talk to green. Very straightforward. Unfortunately, in the world of Kubernetes, where VMs start moving away, you need an object that's built in to be able to support the fact that containers move all around. So in this case, let's say I have red and green, but they're both on the same VM. How do I manage that kind of thing? Or let's say I have red and green on 2 different VMs. How do I manage those? Would I build that into the VM? No, of course not, because the pods could move around, and that wouldn't be any good. So with network policy, it's unfortunately a little bit more complicated than I can write on a slide. Not terribly complicated, but it's just requires a little bit more. But what you would say to the entire cluster is, the first thing you would say is nothing can talk to anything. And that puts in a policy rule. And then you say green can talk to red. And again, this is at the API server level, and you can accomplish this. And this is something that's been contributed to enormously by Tigera as well as other folks. But this, again, you can speak in Kubernetes language. And what that means is that even if now one red pod moved from the VM that was on to a new VM, those same rules still apply. You're doing this at a label-based system, which is extremely powerful and lets you describe it in the way that is important to your application. OK, final concept. Let's talk about complicated installs for apps. Today, you can do a lot of manual stuff. And it's not terribly hard to install, but particularly as applications get larger and require a whole set of different things to support, this can be very challenging. In Kubernetes 1.4 and 1.5, actually, we've done a whole bunch of implementation around Helm, which is the package manager for Kubernetes. Really think, apt-get or yum for your Kubernetes installation. And now it natively supports things like daemon sets, deployments, secrets, all sorts of stuff. Let me show you just two quick examples of this. You have an example here of Datadog. Obviously, this is a daemon set that works across an entire system, but it also requires an API key because you have a personal API key that you might have signed up with for your particular corporation. In this case, you can see the command there for installing Datadog. Very, very straightforward. You say a name, and you set an API key, and off it goes. And it deploys a daemon set across everything. And your system now understands it. It can handle upgrades and all sorts of things like that. Another example I want to show off is Sappho. Sappho's been a containerized application and was actually on launch stage with us, been a big supporter of us for a long time. They're a great, complicated app where they have front-end Tomcat, they have back-end MySQL, and they have a litany of connectors that work with a whole set of external people. What they do is they basically provide a single pane of communication for all these things. Very, very powerful application. As you can see, this is a lot of stuff. To install it, that's the command. So really, really interesting, really powerful stuff. Highly recommended. OK. Let me just give you a quick highlight on something that's launching today. We have a 3-tier solution here from Datera, Tectonic, and Supermicro all together, which have really worked together and are launching a brand new solution that helps really accelerate a lot of the stateful apps that you saw here on stage. So what's next? For those of you looking for Kubernetes 1.6, nothing. There's nothing coming. 4 large values of nothing. I kind of am joking, but I'm kind of not. We've been going at an absolutely torrid pace. And one of the things that we're really going to take 1.6 time is to move a whole bunch of features that we have in alpha or in the current proposal stage and move them into production. So there's lots of stuff coming, but we really are taking a little bit of a breather in 1.6 through the holidays and into the beginning of next year to stabilize a bunch of stuff and give you access to a whole bunch of stuff that unfortunately today is alpha. This includes federated deployments and daemon sets, so you'll be able to use those, again, native Kubernetes objects across those multiple clusters. We have significantly improved RBAC and stateful sets. We're going to have a lot of improved scaling, including contribution from CoreOS around etcd 3, moving up from etcd 2. We'll also have kubeadm for high availability setups. Right now, it's just a single master. We're going to be making it that easy to install high availability Kubernetes. And then finally, an integrated metrics API. So today, you have to do a fair bit of integration with the underlying tools to strip out and get the metrics you want. We're going to have a very clean API that will allow you to attach it. First off, mine the data that's already there, but second, attach it to whatever metrics solution and aggregator you use. And that's it. Again, the net is that Kubernetes is open. We take pull requests. We take contributions. We fly to where you are and help you containerize your application. You name it. Everything happens transparently, and it really is owned by no one. It is owned by the entire community, and we're extremely proud of that.